Yeah.
Uh-oh.
Okay, rational functions. If you're not here on day one, I'm gonna catch you up on just about everything you missed, because it's pretty much a continuation of that. So we have this rational function here, x plus 1 over x minus 3. In order to find the domain of this function, you set the denominator equal to 0 and solve. And if you did that, you would get 3. What that tells you is x cannot be 3. So the way that we document that in interval notation is as follows. Boom. Let's see if we remember from last class. So is this going to have any holes in the graph? Anybody?
No.
No. You know why?
No.
Love the answer.
Because 9 is squared.
Okay.
And it's 1 over 1.
Okay. Here's how you can tell whether or not you have holes or not. You have to have factors that cancel one another out. We don't have factors that cancel one another out, so none here. Now to find your roots or x-intercepts, set the top equal to 0 and solve. And if you did that, that would give us -1. -1 comma 0 is our x-intercept there. Vertical asymptotes. In order to find your vertical asymptotes, set the bottom equal to 0. We've already done that. We would get 3. So x equals 3. Vertical asymptotes. Now, tangency or togetherness. Here's what you're looking for tangency or togetherness. Do you have any parentheses that are being squared? We don't. So we don't have an example of that with this function. Now, end behavior asymptote, most of the time, it's going to be a horizontal asymptote. And the way that you determine that is you want to look at your x values on top of the fraction and bottom of the fraction, and then compare them. We have x over x, exact same. That's even distribution. So look at the numbers in front of them. 1 over 1. 1 over 1 is 1. So our ends behavior asymptote is y equals 1. And then lastly, in order to find y-intercept, everywhere you see an x in your function, you're going to plug in a 0 and then do the math. Well, that would simply leave us with 1 over -3. -1/3 is our y-intercept. Now we have just enough information to graph, so let's do that. I prefer starting with my asymptotes first, just so I don't forget. So that's what I'm going to do. X equals 3. So a vertical line going through the x-axis at 3. And then y equals 1. Horizontal line going through the y-axis at +1. Now we're going to plot any points that we know. We know what the x-intercept is, -1 comma 0. Let's see. We also know what the y-intercept is, -1/3. I'm just going to put it right in between 0 and -1. And now these 2 points are, they're kind of curving together like this. So that gives us an idea of what this graph is going to do. Blink. See that? It's hovering right by the asymptote, and then as it begins to merge towards those points, it then approaches the other asymptote. Since there's no togetherness or tangency, that means the diagonal portion of this is going to look pretty similar. So we can just sketch what we think it would look like. Okay, for domain, once again, set the bottom equal to 0 and solve. If you did that, we would get 3. So that tells us that x cannot be 3. See if you can fill in the interval notation. Try that. If x cannot be 3, what will the interval notation look like? How'd you do? Yeah. Is it really? It's the same as the top.
Yeah.
I didn't realize
That's
that.
what I said.
Next, holes. Do we have any? How about no? No, we don't. Because we don't have any factors to cancel. X-intercepts, what do you think?
Oh, wait, sorry, -1.
-1, good. Set the numerator equal to 0 and solve. Now you just said 3. What did you give me?
The asymptote.
You gave me the vertical
That was
asymptote.
what the
Good.
asymptote-
I know exactly what you were doing. I knew you were a little bit ahead. Okay, now, do we have an example of tangency or togetherness here? Yes, we do. Question, because of the square, great. We see a parenthesis that's being squared. So we know we have one of these two. Since this square is located on the bottom, that means we're gonna have togetherness. Your end behavior asymptote, top heavy, bottom heavy, or even. What do you think? Top heavy, bottom heavy, or even? Bottom heavy. And if it's bottom heavy, it's always y equals close 0. There you go. Y-intercept everywhere in your function, plug in a 0. If you did that, that would leave us with 1 over -3 squared, which would be 1/9. Very good. Can anybody, okay, if you can get this movie, you're gonna get some sort of prize. Here's the quote. You have to get the entire title, by the way, because I'm giving away part of it. Very good. Mr. Ventura. Very good. I believe you solved the case.
Johnny.
No, but I like the guess. I said very good, Mr. Ventura. Very,
Wait, say.
Mr. Ventura. Very good. You need the full title. Pet Detective, but it's the second one. No. Okay, here we go. I'll reward you two in just a second. Remind me. Ace Ventura, Pet Detective. I don't know. Actually, I don't know if Pet Detective is part of it, but Ace Ventura, When Nature Calls. Yeah. Now we all remember seeing it. Okay, yes, that's right. Okay. Let's now plot. Vertical asymptote x equals 3. Horizontal asymptote y equals 0. Well, actually here we have a x-intercept at -1, 0. And then a y-intercept at 1/9. 1/9 is somewhere in between 0 and +1. I'm just going to put it halfway in between. Now we have some sort of idea of what this is going to look like, at least on the left portion. Something like that. Now, since we have togetherness, remember, that means the right portion, the right of this vertical asymptote would look similar. Okay. Good. Okay. All right, example 3. Please. What do we have to do with this function first? Factor it. Good.
What's that? Okay, what's that from? I know the word. From the back of my.
Does anybody know?
What?
Matthew, do you know what that's from? Okay.
Oh, God, it's right there.
So who said that? Is that you, Mason?
Oh.
You know what's funny? I watched Rainbow on Sunday again.
Uh-huh.
God, such a good movie.
Yeah,
It reminds me so much of you. It reminds
Do
me-
you know that's why? Do you know? Oh, we're gonna have to pause this for. All right. So coming back, now that we've fully factored it, nothing will cancel. We have no holes, none. Domain. Now, if you restrict the domain here, if you set the bottom portion equal to 0 and solve, you will find that there are 2 numbers that x cannot be, 3 or -2. So that's going to change up our domain just a little bit, or interval notation. Boom. All right, so for our x-intercept, set the top equal to 0 and solve. Looks like we get -1. Vertical asymptotes, set the bottom equal to 0 and solve. We're gonna have 2 of them. X equals 3. X equals -2. Tangency or togetherness, we have no parentheses that are being squared, so none. In behavior asymptotes, top heavy, bottom heavy, or even, what do you think?
Bottom head.
Why do you think that?
Because of like, I guess it's kind of like there's more numbers down there.
Okay. Thank you for that answer. I'm just trying to figure out why do you think that? But because the top is being squared, okay, so 2 guesses, 2 logical, what I think that makes sense to me. Then what?
They're equal.
They're even. Yes. Okay. So it helps to have it in standard form to figure out whether or not it's top heavy, bottom heavy, or even, but we can do a shortcut. If we multiply x times x, we'd get x squared. Over x times x, we get x squared. Those are going to be the highest variables and the highest exponent of this problem. So it's even. It's the same. Both of these would have coefficients of 1. So y equals 1. And then lastly, if you plugged in a 0 there, there, and there and solved, you would be left with 1 over -6. So let's go ahead and plot. X equals 3. X equals -2. Y equals 1. Okay, let's see. Our x-intercept is -1, 0. Y-intercept, -1 over 6. Right about there. Okay, now what we've learned up to this point in this class so far is that if we have vertical, 2 vertical asymptotes, that we're going to have some parabola-looking shape in between them. So this one's going to look a little weird, but it's going to look something kind of like that. And then based on what we've learned in this class so far, if we have a shape that looks like that, then that means these portions would have graphs that look something similar to that. All right, example 4. First thing, make sure you factor. I will warn you, okay? X squared minus 9 is not the same thing as, I'm trying to cover that up. X minus 9 squared, not the same thing. X squared minus 9, that is a difference of perfect squares. It will factor. Over x minus 3, x plus 2. Good. Are we going to have any holes in this graph?
Yes.
Yes, we are. We have a pair of factors that will cancel. Can you tell me what the x value of this hole is going to be? 3. How'd you know that? Bingo. It's x minus 3, set it equal to 0 and solve. Perfect. What I'm now going to do is over here, I'm going to write down what the new function is. This is what we're actually going to be using to answer the rest of these questions from now on. Starting with, well, let's figure out what the y value of the whole is. If we know the x value is 3, we substitute 3 here and here, which would be 3 plus 3 over 3 plus 2, which is 6 over 5. If your graph happens to have a hole in it, here's how you plot it. So we're going to go over to, we're going to go right 3, and 6 over 5 is somewhere in between 1 and 2. So I'm going to put it halfway in between 1 and 2. So right about there. And put an open circle because it's a hole. Now here's what our domain cannot consist of. I'm gonna go back here. I think it's a little bit easier to read it this way. All right, yes, sir. Go ahead. So x cannot equal, if we look at this example here, set the denominator equal to 0 and solve, x cannot be 3 or -2. So our domain in interval notation looks something like this. What? Huh? Okay, your roots, remember, we're now looking here. Set the numerator equal to 0 and solve, that would give us -3. Vertical asymptotes, set the denominator equal to 0 and solve, that would give us -2. Tangency, togetherness, none of these factors are being squared. End behavior asymptote, top heavy, bottom heavy, or even, what do you say? Why do we say top?
I'm sorry.
Even, because we have x on top, x on bottom, x over x.
Yep.
Look in front of the coefficient. Look in front of the x for the coefficient. That's what I meant to say. 1 over 1. So y equals 1. Your y-intercepts, guesses? Three over 2. Yeah, 3 over 2. And now we graph vertical asymptotes, x equals -2. Horizontal y equals 1. Let's see, x-intercept -3, -0, -1, -2, -3. And then y-intercept 3 over 2, which is 1.5. And now we can graph. Okay, for the time being, let's skip over 5. Let's just look at 6. This one is unlike any we've done up to this point, but it's really not too bad. I think you might find this a little bit easier. First things first, factor. Once you factor, you will see that, well, we have a pair of factors that will cancel out, meaning we're going to have a hole in the graph. The x value of that hole is -3. Down here, I'm going to write down what is left over after we've canceled. That would be x minus 3. Bingo, you just told me the y value of the hole. You took -3, substituted it here. That gave us the y value. And I'm going to go ahead and plot that so I don't forget. -3, -6. So right about there. Okay. I'm going to work a little bit backwards. Normally we answer all these questions and then we graph. I'm going to graph first this time because that is the equation of the line. Those are pretty easy to graph. This is what's left over. We just start with the y-intercept, which is -3, -1, -2, -3. And then you could use Ryo's over run. Your slope is x, up 1, right 1, up 1, right 1, up 1, right 1, up 1, right 1. Or what I'm going to do is I'm going to solve for the x-intercept. Set the equation equal to 0 and solve. We would get 3. That's our x-intercept. So I'm going to put a dot there. And now I'm just going to connect. Just make sure you don't go through the hole because, you know, it's a hole. Then include that point. Now our domain is going to be all real numbers except the x value of the hole, which is -3. The roots, we already solved that. It's 3. To find vertical asymptotes, well, you could look at the graph and see that we don't have any. Or put the equation over 1. Well, in order to have a vertical asymptote, there should be an x on the bottom, and there's not. Entity togetherness, none. Now, this might be a little bit different than what we're accustomed to. The end behavior for this one is going to be the equation of the line. And then our y-intercept, we've already done it, 0, comma, -3. Okay, so let's go back to example 5. Okay, so for domain, we're gonna take the bottom set equal to 0 and solve, and that will tell us that x cannot be 3. And it cannot be -4. Poles, we don't have any factors here that will cancel, so none. Now, roots, x-intercepts. This might cause a little bit of confusion because we traditionally set the top equal to 0 and solve. Well, 5 does not equal 0. That doesn't make sense. Therefore, none. We don't have any x-intercepts here. Vertical asymptote, set these two parentheses equal to 0 and solve. You would get 3 and -4. Here we have no tangency or togetherness because we don't have any parentheses that are being squared. And behavior asymptote, you need to identify top heavy, bottom heavy, or even. Well, we only have x values in the bottom, so we're going to be bottom heavy. When that is the case, y is equal to 0. If you plugged in a 0 for x here and here, in order to solve for your y-intercept, you should have got 5 over -12. So now we can begin graphing. I'm going to start with my vertical asymptotes. And then -4. And then our horizontal of y equals 0. X-intercepts, we don't have any. Y-intercept, 5 over -12. I'm just going to put that right in between 0 and -1. Now we only have one coordinate. This one might have been a little confusing, but what we have learned up to this point in this class is if we have vertical asymptotes, we probably have some sort of parabola shape between them, and we do here. And what we've learned so far is that if that's the case, then the remaining portion of the graph would look like that. So that would be your answer for example 5. Example 7, first thing you're going to want to do is factor the top factors to x minus 4, x plus 4 over the bottom factors to x minus 4 over x plus 3. Well, we have a set of matching factors that will cancel out. So our x value of the whole will be 4. I'm going to write down the new function over here. In order to figure out what the y value is, take the x value and substitute it for x in the new function. And if you do that, you should get 8 over 7. Now I'm going to go ahead and plot that now so I don't forget 1, 2, 3, 4, and then I'm going to go to about 1.5. There, the whole has been plotted. Now here, x cannot equal -3. Or the x value of the whole, 4. Or you could have used the original form. Can't be 4, can't be -3. All right, so let's do our interval notation here. Now, in order to find our roots, remember, we want to look at the new function once we canceled everything. So in order to find the roots, set the top equal to 0 and solve. That would give us -4. Asymptotes, vertical asymptotes, set the bottom equal to 0. Tangency or togetherness, none of these factors are being squared. End behavior asymptote, this is evenly distributed. The numbers in front of both of these x's are 1, and 1/1 is 1. Yes, sir. Here we go. Y-intercept. If you plugged in a 0 here and here, that would leave you with 4/3. All right, let's graph. Is he doing okay these days? I wonder. Mr. Malone. I don't know. I thought he's not doing too good. I don't know if that's true or not, but I hope he is. Y-intercept 4/3. I want to put it about 1/2. And now we can graph. All right, example 8. Looks like x cannot be 2, x cannot be -3, so that's gonna help us with our domain. I will, yes. Better?
Yes.
Poles, none. Roots, what say ye? None, Mr. Flores. Yeah, all right, good. Because if you took 7, set it equal to 0. No, it's 7 doesn't equal 0. That doesn't make sense. Asymptotes. X equals 2. X equals -3. None for tangency or togetherness. We don't have any parentheses that are being squared. In behavior asymptote, looks like we're bottom heavy here, so y equals 0. Y-intercept, you should get 7/-6. Let's graph. No, -7/. So right about here. And I will slide this up in about 30 seconds and we'll do the last one. Okay, we look to be good. So let's take a look at example 9. Let's fully factor. Boom, there's a set of factors that are going to cancel one another out. Leaving us with y equals x plus 5. Well, this is the x value of the whole. If we took that, plugged it in here for x, 5 plus 5 is 10. If you got 5, 10, you're like, well, that doesn't even fit on the graph. You did it right. It's okay, it doesn't fit on the graph. 1, 2, 3, 4, 5, just plot it way up here. Now, this one, we did something similar earlier. This is the equation of a line. So I'm just going to graph the line. Those are easy to graph. Our y-intercept is 5, up 1, 2, 3, 4, 5. If you set this equation equal to 0 and solve, we get x equals -5. That's our x-intercept, -1, -2, 3, 4, -5. And now I'm going to connect those dots. Man, it looks like I drew that one like almost perfect. Domain, it can be everything except 5. Roots, there it is, -5. Vertical asymptotes, none. Tangency, togetherness, none. In behavior, it's going to be this. It's actually going to be the equation of the line. And then lastly, y-intercept, which we already plotted.